Good afternoon and welcome to the USDA Human Nutrition Research Center on Aging's Monday seminar series. Before introducing today's speaker, let me remind you to ask your questions for our speaker using the Q&A icon located on the webinar toolbar. I encourage you to add questions as they arise during the presentation. There's no need to wait until the end. And each month this year, our seminar series has featured a speaker from the different ARS Human Nutrition Research Centers. And today's speaker is Dr. Jay Chow, a research nutritionist at the USDA ARS Grand Forks Human Nutrition Research Center. Dr. Chow received his PhD in mineral nutrition from the Department of Animal Science at the University of Florida and had postdoctoral training in mineral nutrition and bone biology at the University of Florida and UC San Francisco, respectively. Dr. Chow's research focuses on how nutrition and physical factors affect bone metabolism using both basic and translational research models. Specifically, his research at the Grand Forks Human Nutrition Research Center includes the effects of protein intake and acid-base balance on bone health in humans, and the effects of exercise on bone metabolism in obese animal models. Today, Dr. Chow will discuss his research in a presentation entitled Caloric Restriction and Timing of Exercise on Bone in Obesity and Aging in Animal Models. And now let me turn the microphone over to Dr. Chow.
Thank you, Paul. Good afternoon. It's still morning here. I would like to thank HNRCA and Dr. Both for the invitation. Here, I'd like to share with you some of my work regarding diet and exercise on bone metabolism in obese or aging animal model. Although obesity has been considered a risk factor for many chronic disorders, it has been thought beneficial to bone and a protective factor for osteoporosis in human. The alleged beneficial effects on bone are mainly based on assumption that greater body weight would provide more mechanical loading and increase bone formation. Indeed, increased mechanical loading, for example, like exercise, has been proven to be the most effective way to increase bone mass and strength. However, data over the past decades in animals and humans demonstrate that increased fat mass is inversely associated with bone mass. Studies also show marrow adipogenesis, as seen in obesity and aging, is inversely related to osteoblastogenesis. Bone is a dynamic tissue that undergoes significant turnover throughout the lifespan, involving bone resorption and by osteoblasts and bone formation by osteoblasts. Obesity can negatively affect bone through multiple mechanisms. For example, through decreasing osteoblast differentiation, or through increasing pro-inflammatory cytokine, therefore increase osteoclast activity, increase bone resorption. This table shows some evidence that supports an inverse relationship between adiposity and osteoporosis. High-fat diet-induced obesity is mainly in animal model. And on the other hand, physical activity and IGF-1 treatment decrease adiposity and increase bone mass. Using a high-fat diet induced obese animal model, we and others demonstrated that obesity reduced bone mass by increasing osteoclast activity, and despite increased bone marrow's osteoblast differentiation formation, also despite insignificant increase in body weight. This effect not due to the difference in intake of other nutrients, because the diets were formulated based on energy. High-fat diet you see based on energy, it's the same as the control normal fat diet. And weight reduction is recommended to reduce obesity-related health disorders. This can be achieved by either reducing energy intake and calorie restriction, or increase energy expenditure, such as increased physical activity or exercise. It is well known that physical activity exercise benefits bone mass and strength by promoting bone formation and decrease bone resorption. Here, I like to present some data of 2 animal studies in this area from my lab. The objective of the first study was to determine the differential effects of calorie restriction and or exercise on body composition and bone. About 78 male SD rats, 6-week-old, fed either a normal fat diet containing 10% energy as fat, or high-fat diet, 45 energy as fat for 3 months. Then rats on the high-fat diet either continue on the same diet or started on different calorie restriction or exercise protocol for an additional 3 months. Total experiment lasted 6 months. Rats in the exercise group underwent involuntary exercise using motor-driven running wheels at 9 meters per minute for 2 hours per day over a 7-week period. The experimental design is shown above, and diets were formulated based on energy to prevent difference in nutrient intake for caloric restriction groups. Calorie restriction diets were adjusted to have higher content of minerals and vitamins, as shown in this table. And compared to high-fat diet group, rats given high-fat diet plus calorie restriction at 8 and 16%, or high-fat diet plus exercise and with 8% calorie restriction, except high-fat diet plus exercise alone, had lower fat mass. There was no difference in lean mass among high-fat diet treatment groups. Compared to the high-fat diet group, calorie restriction not with exercise significantly decreased the serum leptin. Rats on the high-fat diet with calorie restriction and or exercise had lower serum TRAP and tartrate-resistant acid phosphate compared to high-fat diet alone. indicating decreased bone resorption. Calorie restriction at 16%, but not with exercise significantly decreased serum IGF-1. In conclusion, from the also bone structure analysis revealed that calorie restriction, but not with any exercise groups, such as high-fat plus exercise or high-fat exercise with 8% calorie restriction, decreased bone mass at femoral and lumbar vertebrae compared to high-fat diet group. In conclusion, calorie restriction combined with exercise is effective in reducing adiposity and mitigating bone structural deterioration in high-fat diet, fat, obese rats. Previously, we showed that involuntary wheel running improves but does not fully reverse the deterioration of bone structure of obese prone rats despite decreasing adiposity. For those two studies, rats exercise during light on, i.e. rest phase for rodents. We don't know if exercise during light off, i.e. active phase, would produce greater anabolic effects on bone than the rest phase exercise, i.e. without disturbing animals' normal sleeping. So we conducted another study determining timing of exercise on bone metabolism. Many biological processes and physiological functions of mammals display biological or circadian rhythm, such as sleep and weight, fast and feeding, body temperature variation, hormonal secretion, and locomotor activity. These rhythms are controlled by a circadian clock. Disruptions of biological rhythm contribute to many health disorders in humans, including osteoporosis and bone fracture. Bone cells expressed clock genes. About 1/3 of the genes expressed in mouse calvario bone show a rhythmic expression comparable with those observed in brown or white adipose tissues and liver, measured by gene array. Bone resorption and formation exhibit diurnal rhythm. In humans, plasma concentrations of bone resorption marker CTX is greatest in the early morning and lowest in the afternoon. Similar pattern has been observed in rodents, but with a reverse light cycle. Disruption of the rhythms can lead to imbalance of the bone resorption and formation and bone loss. For example, 3-week sleep restriction induced circadian disruption leads to uncoupling bone turnover, in that bone formation is decreased while bone resorption is increased. Night shift working is associated with low bone mineral density and increased bone fracture. And bone the disruption bone resorption, the disruption of the the timing of exercise has been shown to influence physical functions. In humans, like, for example, exercise before breakfast increases fat oxidation over the next 24 hours compared to exercise is performed in the afternoon or evening. Butchert in 2022 demonstrated that mechanical loading of tibia of mice at early active phase, like ZT14, increased the endocortical bone formation and decreased the expression of sclerostin and DKK. Both are Wnt signaling inhibitors in young mouse tibia compared to loading at the rest phase, ZT2. However, the extent to which the timing of exercise alters bone structure and metabolism in older animals has not been investigated. Therefore, we conducted an animal study to investigate whether the time of day of exercise alters the beneficial effects of exercise on bone, especially bone structure. We hypothesized that exercise during the active phase would result in greater bone mass than those exercise during the rest phase in older the animal. In this study, 55 female 12-year-old SD rats were randomly assigned to 4 treatment groups. Rats were subject to no exercise or 2-hour involuntary exercise per day, 5 days per week for 15 weeks using motor-driven running wheels. This exercise protocol is the same as our previous study. ZT0 is defined as light on, the start of the rest phase for rodents. The ZT4 to 6 is considered rest phase. 12 to 14 is the early active phase. And ZT22-24 is a late active phase. A red lamp was used at minimal intensity during the active dark phase exercise period, i.e. The ZT12 to 14 and 22 to 24. Rats were housed in 3 separate rooms. The on and off light cycles for each room were set individually and automatically to allow us to perform exercise, animal care, and other experimental procedure during the work hours, daytime work hours. Light intensity was the same for all rooms. The exercise protocol was considered, moderate exercise for rats. To minimize the effects of timing of euthanasia and on endpoint measurements, rats were sacrificed to collect samples between 9 a.m. to 11 a.m. with a similar number of rats from each group on 3 consecutive days. This study actually was conducted during pandemic. It took us several supporting staff helped them dearly. And we found exercise at different ZT did not affect body weight, fat mass, and lean mass. And poor exercise groups had a greater IGF-1 and irisin, mitochondria compared to no exercise group. Expression of circadian genes were not affected by either exercise or time of exercise. As you can see from this table, exercise, but not timing of exercise increased the tibial bone volume over total volume, connectivity density, and decrease structural motor index or increase the cortical thickness of the tibial mid-diaphysis. In conclusion, we found exercise improved tibial trabecular bone structure in aged female rats. Exercise increased the serum IGF-1 and the irisin concentrations. The time of exercise did not significantly affect bone structure or bone-related biomarkers. In discussion, in our previous two studies with a similar number of animals in each group, about n equal 14, we demonstrated exercise for 12 weeks decreased the fat mass and serum bone resorption marker TRAP and improved bone structure in young rats. We only detected difference in bone structure difference between combined 3 exercise groups and no exercise group, indicating exercise has less anabolic effects on bone in older animals. Older animals, rats, were used in this study. We tried to mimic bone deterioration with age and or low estrogen. Older rats could be less responsive to exercise. IGF-1 may play a role in this response. For example, in this study, we found the serum IGF-1 concentration about 600 nanogram per ml versus close to 1,000 nanogram per ml in young rats in previous studies. Therefore, these older animals may need longer duration of exercise to have a detectable effect on bone structure. Previously, we showed that older animals are less responsive to IGF-1 treatment. For example, treatment of older animal has a less bone formation, calcium nodule formation. When these animals treated with IGF-1 at 2.5 milligram per kilo body weight per day for 2 weeks, while young animal, when primary bone marrow cells cultured after treatment, you see dramatically increase. We also demonstrated older animals had impaired IGF-1 receptor activation compared to young animals. This animal study did not support our hypothesis that is exercise in the rest phase, light on, would disrupt animals' normal rhythm and blunt exercise-induced bone anabolic effect compared to exercise in active phase. However, in contrary, Butcher et al. In 2022 demonstrated that the mechanical loading of tibia at early active phase increased the endocortical bone formation and decreased the expression of bone formation inhibitor. compared to loading at the resting phase, ZT2. Although physical activity may have a positive effect on bone in general, different exercise models like treadmill running, wheel running in this case, or swimming, resistance training, all may have different osteogenic effects. Further study is needed for best model to be used. While disrupting animals' normal rhythm, like disrupt sleeping, could be bad for bone along as per se. However, exercise during the rest phase could have a greater suppression of bone resorption, which is high during the early, the late, the rest phase, late sleeping period. So we think extrapolating data from rodents to diurnal humans should be taken with caution. Viewed environmental cues affecting the biological rhythms and the responses to are distinctively different compare animals living in vivarium and those to humans. Such as like light cycle in vivarium, either on and off. Light intensity always constant, humidity constant, noise level or pattern, even diet. Human consume different diets of morning, lunch, breakfast, the dinner, while animal access to the same diet all day long. So from our study, take-home message from these animal studies is that although the degree may vary, exercise is beneficial to bone of animals, regardless of age or when to exercise. Thank you.
Thank you very much. I don't see any questions yet in the Q&A box. I was just curious, because what you saw in the animals, you say it's hard to really translate these animal models currently to humans, but what you saw, that's somewhat inconsistent with what we see in older adults. The fact that the effect of exercise might be diminished as we age.
Pardon?
Basically, you had indicated that really translating the work from the animals to humans is really difficult for many reasons. But again, you had seen in the rats that there was an effect of age on the ability of exercise to affect bone
Yes.
resorption.
Okay. Yes,
Is that consistent with what we see in humans?
I would think yes. I would think yes. All I said is the timing of exercise. When these translate to human would quite different. We need to be carefully design the animal study translates that when to exercise to human. In general, exercise improve bone structure in animal and can be translated to human.
All right, thank you. First question is now in the Q&A box, and it's from Alice Lichtenstein. And she asks, for the high-fat diets, does the fatty acid profile, saturated fat, MUFAs and PUFAs, alter the bone response?
I think the type of fatty acids should have effects on different responses. These diet were formulated based on mostly for high fat diet is lard, from lard. Majority are saturated fatty acids.
Thank you. The next question comes from Larry Parnell, who asks, have you considered metabolomics profiling in order to characterize further the response to exercise?
What?
Have you considered metabolomics profiling in order to characterize further the response to exercise?
That's a good suggestion. We will, yeah.
Okay. Next question comes from Sai Das, who asks, what is the magnitude of the offset of exercise during the rest phase on bone resorption? Is it 50% or greater?
I don't know. It's hard to differentiate. On the one hand, you decrease bone resorption during the rest phase exercise. On the other hand, you may disrupt the normal circadian rhythm. I think further study, careful designed animal study needed to dissect such a difference contribution.
Okay. Next question comes in from Chris Wiley, who says, interesting work, and I love looking at the rat model. I may have missed it, but how does calorie intake or expenditure change with exercise? And how do you separate the effects of energy balance from those that are beneficial due to exercise on its own?
I think in one slide for those the exercise with the restriction, we pair fat either pair fat with the 8% calorie restriction. On top of that, additionally, we exercise those rat exercise. So the food intake for is pair feeding to the corresponding group.
And I think I'll wait a few more seconds, but that may be the last question. I'll just wait a minute to see if anyone else has a question. Question just came in. And okay, Zhendong Wang asks, IGF-1 activity can be affected by its binding protein. Have you looked at plasma levels of IGF binding protein 3 in your study?
That's also a good question. No, I haven't. That's my IGF-1 work with the older animal. That was my work in UC San Francisco, pretty long time ago. Recent study also showed IGF-1 concentration or binding protein may be a link between obesity and neurodegenerative disease. I think would be a link for bone too.
Okay, and one other, not question, but comment, suggestion from Richard Albert, who says, it would be enlightening to contrast the differences between wheel running, cardio aerobic exercise, and resistance weight exercise with all other factors constant.
That's a good suggestion. I think as you see the other study with the loading animal model specifically, I think that's a different. They found the difference between active phase and rest phase. We are running maybe different.
Okay.
Yeah.
And I think that's all the questions. So again, I'd like to thank you very much for
Okay.
an interesting presentation.
Thank you.